It seems appropriate to open up any Calc 2 class speaking about the fundamental theorem of calculus, or sometimes I'll abbreviate it as FTC. And there's really two parts to it. I'm going to give you a condensed version of it. And the first part really has to do with the inverse nature of the two operations. So we'll call this part 1. And that ties integration and differentiation together. So it ties differentiation and integration together. And in fact, right, they are, inverse operations in the sense that if I take the derivative of an integral of a function, that I end up back with the function. So if you want to think of it in these terms, it sort of undoes or inverse operations, inverse operators. And both of the operators, derivation or integration, they're both operators. And once you perform the act of integration or taking the derivative, then those operations go away, much like if you were adding two numbers, 2 plus 3 equaling 5. Right? The addition operator, once you resolve that addition operator, it goes away. I often see students holding on to the integral symbol way too long. The second part has to do with the definition of definite integrals. So what is a definite integral? So let's define that. So if we let me grab a different color here. If we let f be a continuous function on a closed interval, a to b, and big F be any antiderivative of f, then what we can do is define this definite integral. And the definite integral is on that closed, the limits of integration are on that closed interval AB. So I'm going to define these as the limits of integration. And some function with the differential. So we have the integrand, and we have something we refer to as the differential, which tells us we're integrating with respect to the x variable. So we're integrating, I'm going to abbreviate it, with respect to the variable x. So everything needs to be in terms of x, the limits of integration, the function, and the differential. So what the fundamental theorem of calculus is saying for a definite integral is that you would evaluate the antiderivative at the upper limit of integration and subtract from it the antiderivative evaluated at the lower limit of integration. So there are the two parts to the fundamental theorem of calculus. Let's do a quick problem and just kind of review the power rule. So let me go to a new sheet and we'll start with an example that's going from x equaling -2. And I will often drop the limits of integration here, or the x equals, when we actually go to resolve this. Okay. So when we take the antiderivative here, we're going to be using the power rule. So the power rule states that we add 1 to the power and then we divide by that. So we have x squared, so we add 1, that's 3, and divide by 3. And then we have a constant. And notice at this point that this integration symbol has gone away because you performed the act of integration. You found the antiderivative. And then we're going to evaluate this at the upper and lower limits. So often in a problem, I'll pull aside, and I'm going to here, just to do a quick review of a couple of things for you. Unfortunately, I don't have a lot of space on this, but we'll go ahead and we'll pull aside. Let me get a different color here. We'll pull aside the power rule for a moment. And what the power rule states is that if you integrate any power of x's, that you add 1 to the variable and you divide by that. So that, in essence, is the power rule. And you know what? I'll take it a step further and show you the first part of the fundamental theorem of calculus that says if I take the derivative, right, of this integral, now I'm going to replace that integral with the resolve of the power rule. And when I take the derivative, well, what does the derivative say? The power becomes the constant multiplier. You subtract 1. And of course, this p plus 1 is already there. So what do you end up with? You end up with the function you started with. So that is the power rule. So that's what I did here. And notice that with just the constant 4, you can understand that 4 really has an x to the 0 attached to it, because x to the 0 is simply 1, right? Anything to the 0 power is 1. So if you were to add 1 to it and divide by 1, you get that 4x, which is why the constant is resolved as negative 4x. So now let's go ahead and evaluate that. And when we do that, using the fundamental theorem of calculus, we're going to use the FTC here. And when we do that, we plug in the upper limit of integration. Excuse me. And we subtract the lower limit of integration. Keep your sign straight here. So I'm just going to bracket here so you can see that this is f of b minus f of a. Okay, so we'll do the math quickly, and you'll see, keep our sign straight, that this resolves to negative 32 thirds. And you might ask yourself the question, well, why is the area negative? How can area possibly be negative? And that is because when you are integrating, you are finding the net area. So when you integrate, you are finding the net area. Okay, so what does net area mean? Well, the net area is equal to the area above the x-axis minus the area below the x-axis. And if you look at the graph, let's graph this function. The graph of this function, oh why, I could have drawn nicer lines here, is going to look like a parabola opening up, and it crosses negative 2 and 2 at the x-axis. And it turns out that that area, that net area, is all below the x-axis. So therefore, that area should be negative. So that is what I will often call a belly check. right? Make sure that your answer makes sense. If you would have had a positive number, it should fail the belly check because this curve is all below, between -2 and 2, it's all below the x-axis, so it should have a negative area as an answer. And if it turned out positive, then you flipped a sign somewhere, or you had another error somewhere. So always do your belly check, right? Whenever you solve problems, the last question you should ask yourself is, does the answer make sense? Does the answer make sense, right? We always want to ask about sense making. And in this case, the answer makes sense, so we are a happy mathematician.